Hello everybody. Let's see that we have already 55 people. Please say yes on the chat if you can hear me. Great. Hello everyone. Okay, so today we have, these are our learning goals for today. So we will continue with the rendering pipeline. So we will talk about new stages, the clipping stage, the culling stage, the rasterization, and finally the fragment shader. So it's a long way to the fragment shader, okay? But first, I wanted to discuss something with you. I don't want you to have a false expectation on how we can answer your questions on the chat. The thing is, the chat moves very fast, and sometimes people is asking questions that are not related with the lecture. So I'm worried that you might expect that either me or the TA, in this case Ivo, if we can like answer all the questions on the chat. That is probably not possible. Okay, it's not possible for me or the TA. So we still have 2 breaks for questions during the lecture, and we will check today if we can use also your audio by raising your hand on Zoom. If this doesn't work for some reason, we can still use the chat, but only on question time. Okay, so I will ask you again if you can save your questions only for the question time. If you really want to ask something, yeah, you can maybe raise your hand, and we can also try that, right? But let's try to keep those, and even using that time is not even possible for the TA to collect all possible questions from the chat and then basically give those questions to me. So please remember, sorry, that in the end the best strategy is to get your questions and post it on Piazza. Even if you already got your answer, is very good if you can post your questions, right? I am even modifying the slides based on your questions, so it is also good for me, and it's a good feedback. Okay, so let's try that, and I think we can improve the logistics of the course. Great. Okay, so let's start. So on our last lecture, we were talking about tessellation. So we already mentioned that, but it's like I want to make like a very quick recap of what we said before. So we talk about tessellation. We know the tessellation stage. It's in reality, like conceptually 2 stages. In reality is literally 3 stages. And the purpose is to create new geometry, basically subdividing the current triangles or quads to provide a better looking surface, okay? And we said that again, it has 3 sections. So the first one is a tessellation control shader, which defines how much tessellation we want, right? How many steps of subdivisions we want. The next part is the actual tessellator, the one that creates new geometry by subdividing the current triangles or quads. And the final stage of the tessellation stage is the tessellation evaluation shader. That is basically very similar to a vertex shader. It is actually like a vertex shader, but for those new vertices that were created in the tessellator, okay? Again, please don't panic. Remember that a lot of the concepts that we are checking on this pipeline, we are going to explain those concepts in deep on different lectures eventually, right? Yeah, computer graphics is very large, and the rendering pipeline is a very sophisticated architecture. So don't panic. Let's just keep this thing for you. Okay, and also because you already suggested, I've added more text to my presentation. And actually, sorry, I forgot to tell you, the presentation is also on, this presentation is also already on our webpage. So let me just quickly jump to our webpage. Yes. Okay, so here's the presentation, okay? The fragment shading. So you already have it, okay? If you want to download it right now and just take notes. Good. So again, I've added a little bit more text. So yeah, I think it will be better. Okay. So after tessellation, right? This stage in which we can create more geometry by subdividing the triangles, we have the geometry shader, right? And the geometry shader, we already explained that this is something that it can generate new geometry, but not by subdividing the actual geometry, the current geometry, but creating literally geometry from scratch. And we can use this for particle generation, like or water, or yeah, we can create many crazy things. And this is where we basically finished last time. Okay, so now let's talk about the next stage on the pipeline. This is called the primitive setup. Sometimes it's also called the primitive assembly. Okay, so this stage basically organizes the vertices into their associated geometric primitives. So if you remember, when we were talking about the vertex shader, I said that the vertex shader don't have connectivity information, doesn't have connectivity information, right? And namely, each vertex is basically connected with other vertex in the mesh, right? And the edges of a mesh are also connected with other edges, and yeah, that is basically the topology of the mesh or the connectivity information of the mesh. So that information is not is inside the GPU, but is stored like internally on the GPU, but is not used in the vertex shader. So basically, what the primitive setup does is recovers the connectivity information, because at this time, so vertex data, vertex shader, the tessellation, and the geometry shader, all these sections here are working exclusively on vertex level. Okay, so the primitive setup is the one that recovers that connectivity information that is stored internally and basically creates new triangles or quads, and basically prepares everything for the next stages, which is the clipping and cooling and rasterization. So then we have this stage here, cooling and clipping. It is conceptually is the same stage, because conceptually the purpose of this stage is basically to discard geometry that is not visible to the camera, right? So in the end, we can have several cameras on the scene, right? But we only render a single camera at a time, right? So for the camera that we are working, right? If there is whatever millions of polygons that are outside the view of the camera, like it doesn't make any sense to compute those polygons, right? So basically the goal of this stage is discard useless geometry. And it's divided in two sub-stages, cooling and clipping. Clipping is always there, but cooling is optional, okay? So I will explain first what is the clipping, okay? But before explaining what is the clipping, let's first understand what is the input for clipping, okay? So before clipping, let's imagine this. So first, let's do this quick recap that we have a 3D model. So in this case, we have this bicephalous bunny, this very weird creature here. And we have the model and we have a camera, right? So these objects are inside an Euclidean 3D space, and they have its position, directions, and everything, right? And the vertex shader, once the vertex shader is done, what we have is the position of all those vertices on the screen coordinates, right? On the screen space. Again, maybe right now for you, it's kind of confusing what the screen space is, because we haven't explained coordinate systems, but don't worry, just keep in mind that it's basically saying that the vertex shader will give us the position of every vertex, not with respect to the center of the world, which is basically the center of this cross here on the ground, but with respect to the camera, okay? And with respect to the orientation of the camera. That is basically the screen space, okay? Converting all these vertices positions, right, into the actual coordinate space that is represented by the camera. Okay, so having that, let's imagine that in this case, for example, the camera is very close to the model, right? So we could, for example, activate the tessellation stage to get a better looking surface. So this model in particular is very coarse, right? The triangles are very large. And if we are making a render like so close, yeah, the surface will look kind of ugly, right? So we can, for example, ask the tessellator to increase the number of vertices, right? So this will be the change, right? In this case, we have a certain number of triangles, and if we apply one level of tessellation, basically we have more geometry, and it could be a little bit more appealing, okay? At this point, remember, we are still working on vertices, right? Of course, the image I am showing here, it has triangles. I am showing triangles, and I'm showing even colors, right? But this is only for visualization purposes. In reality, in terms of coding, what the GPU is processing at this moment is only vertices, right? It doesn't have the notion of triangles, not yet. Okay. So once we have once we could have this tessellation stage, because remember that the tessellation stage is also optional. That is something super important. The tessellation is optional. If I don't want to create new geometry, I just don't activate the tessellation stage. So then the primitive stuff will get the connectivity data that was stored internally on the pipeline, and it will again organize the vertices into their corresponding triangles. Okay, so that is a primitive setup, and that is basically all that is happening before the clipping stage. So now let's talk about the clipping stage. So the clipping stage works by discarding or cutting the triangles that are outside the frustum. And the frustum is basically a truncated pyramid. It's basically this shape here, right? So this is the camera, and this frustum is a truncated pyramid that represents the field of view of the camera, okay? This is the space in 3D that is visible to the camera, okay? It usually has a near plane, so we usually put a plane from which every geometry that is closer to that plane, it will not be renderable. And we also have a far plane, the same. We usually put a far plane, and every geometry that is farther than that distance, we will not render that. I think I explained in the previous lecture that this could be useful, for example, in video games. If you're rendering in real time, for example, a city, right? And you can have this like a fog effect. So you could have millions of buildings, right? But the buildings are super far. You can kind of like fade the image of those buildings using a fog effect, and eventually you get like the maximum distance of your fog effect, where basically all the objects are already invisible. So you get that distance as your far plane, and every single geometry that is farther than that, it will be basically discarded from the GPU. Okay. So this truncated pyramid, right? Again, it has a near plane and a far plane, but it also has a top, bottom, right, and left planes, right? So these will be like cutting planes from which we will get either if the vertices that are or the vertices on my model are inside this clipping planes or outside these clipping planes. Okay. So every triangle that is outside the clipping planes it will be either removed or cut it. Okay. So once we perform that is actually the clipping process. So basically, it's just cutting your model and discard every single vertex or every single triangle that is basically outside. If a triangle is completely outside the frustum, it will be literally discarded. If a triangle is at the middle, right? Imagine that a triangle could have a certain area of the triangle inside this volume and a certain part of the triangle outside the volume. In that case, we will just cut the triangle and create new vertices. Okay, but again, we will have a single lecture. We will have a complete lecture talking about clipping. So don't worry, we will explain all those like cutting processes. Eventually. Okay. So that's it. This is the clipping process. Then there's the second process that is optional from this stage, the sub process that is called cooling. Okay. So again, cooling is optional. It's an optional state, and it can discard triangles that are basically facing away to the camera. Okay. So the camera has a view direction. In this case, it's this green arrow, right? So we have a view direction from the camera, and each triangle on the mesh has a normal, right? If you don't remember what a normal is, normals are basically unitary vectors that are perpendicular to the surface, right? And we compute it using the cross product. And again, I'm adding all that text, so you have more information now in my slides instead of just me verbally explaining everything. And what we basically do is we take a cross product between the view direction of the camera, this vector that represents the view direction of the camera, and each triangle's normal, okay? So if we have the, something that is important, sorry, is different technologies define the vector from the camera, they define it differently. So in some videos, for example, sorry, in some books, for example, they define this axis from the camera as the plus z axis, sorry. And in some other technologies, they define it as the negative z value, or the negative z axis, okay? In this case, I am defining it as a positive value. So imagine that in this case, in order to see or to compute which triangles are facing the camera and which triangles are facing away from the camera, I compute the dot product, right? And if the dot product is negative, right, it means that the normal is basically opposite, is exactly opposite to this view direction of the camera. It means that the triangle is actually seeing the camera, right? So once we compute that, we can identify the back-facing triangles, and we can remove them from the pipeline, okay? So those triangles are basically triangles that are not visible to the camera because they're facing away from the camera. And this is the result. And it can look very weird if we are seeing the object from another point of view, but from that camera in particular, with that field of view, the result will be perfect, right? Okay, so now I will switch very quickly to trees to the max, because I created this scene for you to a better understanding of these concepts, okay? So please say yes in the chat if you can see this trees to the max. Perfect, okay. Okay, so what I created here is basically this the same scene that we are seeing on the slides, right? But I have some buttons here that I can use to show you the different steps. So let's imagine again that I have this scene, I have the bunny, I have the camera, and the camera is actually moving, right? So let's pretend that we move the camera very close to the bunny, right? And we can see the camera, and this is the frustum, right? This truncated pyramid. This is the near plane. This is the far plane, okay? So this is the original model. So first step that we discussed is imagine that in this case, for example, because the object is very close to the camera and it will look kind of ugly because it doesn't have enough resolution, we could, for example, activate tessellation and tessellate the geometry, right? So now the bunny looks a bit better, okay? Again, tessellation is optional, but we can ask OpenGL to perform those operations. We know already also that the second option, the other optional stage after the tessellation is the geometry shader. That is also optional, and I said the geometry shader is the one that we can use, for example, to create new geometry from scratch. It can be like particles, water. It can put hair on this bunny, right? But for visualization purposes, I am not adding any new geometry with the geometry shader. Let's imagine that in this case we are not adding anything with the geometry shader. Okay, so then we can show the clipping planes. Okay, so these are the clipping planes. Basically, the sides of the frustum that we will use to discard these triangles from the bunny, right? So then we can perform the clipping, which is basically cutting those, right? Because again, if they are outside this truncated pyramid, it doesn't make any sense to actually render those, right? Great. Now I will show you the normals. And here we can see this thing about the normals. Let me just maximize the view also. Okay, so this is, again, this is the view direction from the camera. I am not showing all the normals from all the triangles, right? Because it will be crazy. I'm just showing a tiny sample of the normals of this surface, right? But in fact, each triangle, well, each vertex actually will have its own normal. Okay, so just imagine this bunny with thousands and thousands and thousands of little arrows, one arrow on each vertex, basically defining the direction that is orthogonal to its surface, right? But yeah, again, just for visualization purposes, this is just a fragment of the real amount of normals that we have here. So basically what I want is, I want triangles whose normal is opposite to the camera. And again, this is depending on how do you set your camera coordinate system. If you set your camera coordinate system in a way that the positive direction of your camera is to the other side, it means that your dot product needs to be 1, right? Sorry, it needs to be positive to keep triangles. In this case, because I am defining on this direction, right, the dot product from the normals and the view direction of the camera needs to be negative for me to know that they are actually seeing the camera, right? And yeah, so remember, if two vectors are exactly the same, the dot product will be 1. If they are at 90 degrees, the dot product will be 0. And if they are exactly opposite, the dot product will be -1, right? So basically, either having dot products either positive or negative, you can compute which triangles you pretend to discard. So let's show the back facing. So here we can see in red all the triangles whose normal is basically not visible from this camera. Okay, there are a lot. So now we can show the culling, and this is basically the final result, right? And again, it looks very weird from other sides, but it will look perfect from the camera view. Okay, so I will come back to the presentation, and let's have a quick note-taking break and questions. So let's try. Yeah, okay, someone is raising hand. So let me check. How can you? Okay. How can I activate your Ivo? Can you help me to activate? Oh, you're here. Sorry. Okay. Unmute. Yeah, William.
Hey, I just had a question about the primitive setup.
Yes.
In WebGL, when you draw arrays, is that the primitive setup?
When you draw arrays?
Yeah, like not in 3JS, but when you're...
Oh, I see. Yes, I think, yeah. If maybe I'm wrong, but yeah, I think you're right. I think, yeah, that is the instruction in which you are literally sending, basically activating that stage on WebGL. Yeah.
Right. Okay. And also, if you do the tessellation shader,
yeah,
wouldn't there be like a primitive setup, or like an early primitive setup, so you can have the triangles to tessellate?
That is a very good question. Yeah, the thing is, the tessellation process is very complicated, and we might talk a little bit more about that, but yes. Okay, you're totally right. The thing is, in order to tessellate something, in order to tessellate a triangle, you actually need connectivity information, right? So yes, at that point, you need to get the connectivity information to know which vertices are connected with which other vertices and which, like, who is actually creating triangles. Then you subdivide the triangles, right? And then you compute everything, everything else. The thing is, when I said that in the vertex shader doesn't have connectivity information, I'm not saying that the information is completely lost. The connectivity information is there. I mean, internally, the GPU knows which triangles are creating which vertices are creating which triangles. The thing is, the vertex shader is a shader that we can program, we can code, right? So the connectivity information is not open for us on the vertex shader, right? Basically, it's not there on the vertex shader, right? On the part that we as humans can code, but it is for sure internally on GPU. So yeah, of course, the tessellator needs connectivity information. It needs to create those primitives for then coding those primitives, and yeah.
Cool. Thanks.
You're welcome. Then okay, so Mark, give me just mute.
Okay, hello.
Hello.
I'm just curious, when you up the tessellation, are we increasing the number of vertices as well? How do we approach that idea?
Yes, exactly. So let me just go back to this, to the tessellation image quickly. But yeah, you basically create new geometry, so you have more vertices. So yeah, so look at this, for example. So here we have a certain number of quads, right? And by subdividing everything, by tessellate everything, we have obviously more quads and yes, more vertices, right? So yeah, the number of the geometry increases. There are a lot of tricks. So for example, if you perform a tessellation, a dump tessellation, basically, actually, let me show you something. Let me show you the trees to the max again. But it's a very good question because it leads to something very important. Okay, so I will show you the original one. Okay, so this is the original one, right? So what I did here, and again, I did it only for visualization purposes. This is a very dumb tessellation because here what I'm doing is I'm tessellating every part of the geometry, okay? That basically increases the amount of memory I need inside the GPU because I am just increasing the number of vertices, right? The number of triangles and the number of everything else. Remember, the last part of the tessellation, it also needs to recompute the normals and the vertex color and everything, like interpolate and everything, and just increases a lot. So what you usually do in a very smart tessellation way in a GPU, and that can be done automatically by OpenGL and also DirectX, is that in fact the tessellation can happen depending, for example, if the model is closer to the camera or not. So imagine, again, I don't have that visualization here, but I might do it for the next lecture. Imagine that instead of just tessellating every part of the surface the same, you tessellate more samples on the parts that are closer to the camera, and you don't tessellate the parts of the camera that are like very, very far, right?
I see. So it was kind of like that point cloud example that you had where there were larger or higher numbers of vertices closer to the camera
Yes.
and more tessellation there.
Yes. So basically, the best tessellation works like this, and this is a technology that is, I think the first technology that did that was DirectX. So the best tessellation is the one that basically you tessellate the triangles at the point in which the final triangles that you have in your 3D model on the GPU are a little bit larger than a single pixel. But that is basically using the screen coordinates, right? So basically, if a triangle is very, very far, right, that triangle is maybe already very tiny with respect to the screen, and is maybe already to the size of a single pixel, right? So you don't tessellate that triangle. But if a triangle is very close to the camera and is basically taking a lot of pixels on the camera, you tessellate that triangle a lot of times, a lot of iterations in a right, and so the final triangles after that tessellation are almost as tiny as a single pixel. So basically what you see is like a gradient of tessellation, and it's really nice because in the end you can keep the triangle counting very low, right? And you can like visualize super complicated scenes with a lot of yeah.
Yeah, that's good explanation. Thank you very much.
Good.
Thank you.
Okay, then we have one more. Pavel.
Hi, I had a general question
Yes.
about when you were saying that the cutting and culling, it should be the process after tessellation and vertex shader.
Yes.
Can we not do it at the time of doing that vertex shader and tessellation to just be more efficient? Because now you just shade everything and tessellate everything and then cut it and cull it. Can't we do it simultaneously too?
Very good question. The thing is, the pipeline on on WebGL, the stages have order, so I don't think it's possible. I'm not sure, but I don't think it's possible to clip before tessellate. But again, the thing is, you need to understand that the tessellation process is optional, right? So it doesn't mean that we always tessellate and we'll always do geometry shader. Maybe you can make a trick. No, maybe it's possible. Yeah, because in the end, the thing is, um, what you could do is maybe start on OpenGL, sending data to the vertex shader, then sending everything to a calling. Yeah, basically skip tessellation and skip geometry, then send everything to the primitive setup and calling and clipping, and then you could get that that data, and instead of continuing on the pipeline, basically like resend that to like another pipeline to tessellate. Yeah, I think, yeah, again, I'm not sure if it's possible, but also if you want to have like something super efficient, remember that before the vertex data, before sending information to the vertex shader, we have the application stage, right? And in the application stage, you also perform certain optimization level, right? So that is what I explained, for example, when I talk about voxels. If you have a geometry that is basically describing a voxel as space, you don't send the thousands of cubes that you have as voxels, right? You don't send those thousands of voxels to the GPU, just waiting for the GPU to cool and clip everything that is not necessary, right? You at the CPU level use your voxel information to construct a polygonal mesh that is super efficient already, and then you send that to the GPU, right? So yeah, and I think in the end, if it's too bad, you probably do it at the application stage. So you only send the the real important information to the vertex shader. Yeah. Okay. So Andrew, I will unmute you. No. Is someone else raising hands? Not. No. No. Okay. So no more questions with hands. Okay. So let me check the chat. Sorry. Um. Okay, guys. So any more questions? Can you, because I think Ivo is actually answering a couple of questions. Anyone else?
I think there's a question I haven't. It's could you attempt to derive the connectivity information through the normals alone?
Oh, sorry, I didn't understand your question. Can you repeat?
It's it's from chat. It says, could you attempt to derive the connectivity information through the normals alone, i.e., if the dot product between neighboring vertices is positive, you can assume they are connected?
No, that is not possible. No, you cannot get connectivity information from the normals. Now the normal is just a vector, and it doesn't tell you anything else but the direction that is orthogonal to that vertex. There's no way to get the connectivity. The connectivity is for a vertex is basically like the pointers to the vertices that are on its umbrella, right? So yeah, no, it's not possible. But again, remember, the vertex shader doesn't contain the connectivity information, but you can you can send information to the vertex shader, right? We can send uniform variables to the vertex shader. So let's imagine, for example, that I want to color the vertices depending on how many neighbors they want. Okay, so the amount of edges connected to a vertex, it's called valence. So the valence of a vertex is the number of neighbors this vertex has. Okay, so I could say I will color the vertices depending on their valence, right? So if a vertex has only 4 neighbors, for example, it will have a different color than a vertex that has like 15 neighbors. So I can send that, for example, as, sorry, I said uniform variable. No, uniform variables are global. So you can, for example, send the valence of your vertex as an attribute variable to your vertex shader. In that case, you have connectivity on your vertex shader, and you could use the connectivity in your vertex shader to modify the vertex color or the vertex position or whatever, and maybe transfer also that information using a variant variable to the fragment shader. But yeah, okay, so I will continue. So we were, but great questions, by the way. Yeah. Okay, so this is calling. Okay, so now let's go to rasterization. We already talked a little bit about that. So the rasterization is this stage that basically generates the fragments of each triangle and assigns their interpolated values. Okay. Again, don't worry, because we will have, if I remember correctly, we will actually have an entire lecture regarding rasterization, because it's a big topic and there's a lot of math involved. But for now, this is a good explanation, right? And we already know what it does. So we have triangles already, right? And basically, remember, the fragments are the portion of the triangle that is basically on the position on the screen in space is in the same position of a specific vertex, right? And let's remind for a moment what this interpolation means, right? So in the case of the normals, for example, instead of having the normals computed from the mesh from the faces, and basically for every fragment having exactly the same normal, what we usually have is we have a normal per vertex, and we have an interpolated value for all the fragments, an interpolated value between them. Okay, and we usually say linear interpolation when we are like in the first stages of lectures like this, but someone already asked on Piazza, and in fact, it's not exactly linear, but the thing is that is also something very complicated, and we will talk about that, about the actually non-linear interpolation that we usually do, but we will talk about that when we talk about the texturing. Okay, so after the interpolation, it will look like this. Well, before, this is what we have, right? So basically, we discarded already with cooling or clipping. We discarded all the things that we didn't want, but at this time, the information is still in like vertex version. Okay, so after the interpolation happens, you will have something like this, right? The normals that in this case are used to define the color of each fragment are now interpolated, right? So not all the fragments from the same triangle have exactly the same normal, so now they are interpolated, and this is basically what you could have as a final image. Okay, so after this, we finally get to the fragment shader, right? So it's a very long road from the vertex shader to the fragment shader, with a couple of optional stages in between. Okay, and by the way, every time you see shader, the word shader, it means that you can code that, you can play with that stage. Specifically for your assignments, you will only need vertex shaders and fragment shaders, but the tessellation and the geometry shaders are parts that you can also play with, and you can also write your own code. Okay, so let's talk about the fragment shader now. So the fragment shader, what basically does is it needs to compute the per pixel lighting and shading, or per pixel or per fragment actually, and it also does the texture mapping, right? So in terms of input, the fragment shader can get the shared varying variables that you can introduce in the vertex shader. So for example, in the vertex shader, you can create a varying variable that holds, for example, a vertex color. And inside the vertex shader, you could modify the vertex color depending on the position of that vertex. So let's imagine, for example, that I can send to the vertex shader also the position of the camera, okay, and or the position of a different object. For example, in your assignment, you have a 3D model, but you also have like a remote control that is basically like a tiny sphere, right? So you can send the information of the position of that sphere. And inside your vertex shader, you can modify the vertex color depending on its distance to this remote control, okay? So maybe if they are closer to the remote control, they will be red. If they are farther from the remote control, they will be blue, and you code like a gradient of vertex color, right? If that vertex color is a variant variable, you basically can get that variant variable on the fragment shader, because variant variables are shared between vertex and the fragment. The difference is that the variant variables that the fragment shader gets from the vertex shader are already interpolated, right? Remember, right? Variant variables are interpolated, sorry, in these previous processes, right? It can also get uniform variables. So remember, the uniform variables are variables that we can send as user. We can send to the vertex shader, but also to the fragment shader, but they are usually global, okay? They're global for everyone. So for example, the position of this remote control in your assignment, it's a global variable, right? Because the position on the world for that sphere is basically the same for every vertex, right? It doesn't change. Okay, and so those are the inputs. And it also has like built-in input variables, which are the frag chord, the front facing, and the point chord. GL frag chord, GL front facing, and GL point chord. So what are those? So GL frag chord is basically the location of the fragment in window space. So the X, Y, and Z components are the window space position of the fragment. And that is obviously very, very simple, right? In the end, we know the fragments are the portion of the portion of the triangle that is basically on the same position of a specific vertex, right? So basically, this is the coordinate of the fragment in that space is basically this input variable. Then we have another Boolean built-in input that is the front facing. This one, it's give me a second. This one is false if the fragment is generated by the back face. So basically, remember that we said that we have this cooling stage, and that cooling stage is optional, right? So it is optional if we want to use it for discard geometry, but we also can use it to maybe not discard geometry, but to recover the information that a triangle, for example, is facing away from the camera, and because maybe I want to change the color. This is actually very, very this is very common to use in computer graphics research, for example. So in geometry processing, we usually have meshes that are open, right? So the bunny that we were seeing is a mesh that is closed, but it can be open, right? It can have holes. So we usually want to visualize those meshes, for example. We usually give a different color to the triangles that are back facing. So it's easier for us as researchers, for example, to open a 3D mesh with holes and identifying like which parts are actually like the inside of the mesh and which are the outside of the mesh, because basically the inside, the triangles that are facing away from the camera, we are rendering those triangles but with a different color. So this option is very useful for that. And then the point chord, this one is a bit tricky. This is the location within a point primitive that defines the position of the fragment relative to the side of the point. The thing is, remember that we can, in OpenGL, we can render triangles, but also we can render lines or we can render points. I show you an example in which instead of rendering the bunny, I was rendering only the vertices of the bunny, right? So that is, you can do that, for example, to visualize like a point cloud of the bunny. So when you want to do that, when you are rendering the vertices, not the triangles, basically this coordinate tells you the position of this fragment with respect to the point that is associated with that point, with that the vertex in particular. Okay, yeah. So this is used when you basically do point cloud rendering, and the output is basically the main output is GL frag color. That is basically the final color of that fragment that eventually it will be a new pixel. Okay. It has other outputs, but that information you can check it on the OpenGL reference book that is already on your on the web page. And this is basically a minimal fragment shader. Fragment shaders can be super simple. Basically, just outputs the color, and that's it. But again, remember, you can get information from the vertex shader. So in this case, for example, I can have variables that are coming from the vertex shader that I can play with those variables to define a different color based on the position of the vertex, based on different things. And we will have 2 entire lectures talking about shading, but not shading in terms of coding a part of the GPU pipeline, but shading in terms of literally painting the color of the pixel based on lighting and materials. Okay, that is done on the fragment shader, and your third code assignment will be related with that. In your third code assignment, you will need to code different shaders to visualize different specular colors and different materials depending on the position of a light and the position of the camera. Okay, that is totally done on the fragment shader. Okay, and the last step of the pipeline after the fragment shader is this stage called per fragment operations. Okay, but we finished today, so that part will be for the next lecture. Okay, and basically we'll have another quick break for questions. So again, if you want to raise your hand, we can answer questions. Anyone raising hands? Yes, Nam, perfect. Let me unmute you. Okay, unmute.
Hello.
Hello.
Hi. I think I asked this question in the chat already, but so my understanding is rasterization will give you an array of fragments, and the fragments are discretized points that have essentially the shape of the triangles, but they're discretized into basically very small fragments, for the lack of a better term, I guess. Okay, so my question is, so you're saying that's done with respect to each vertex. So first of all, how do you assign which vertex one fragment belongs to? And secondly, so if that's true, do many fragments share the frag coordinate, which points to a vertex, but inside that vertex's local coordinate frame, do we get unique point coordinates? Is that how the system works?
Okay, give me a second. Just let me go back. Are you talking about these variable point coordinates?
Yeah. So
Okay,
you're saying a fragment is associated with a vertex, but one vertex can have many fragments. Is that right?
Yes, exactly. Okay. So if you
So
remember,
how does
if you remember,
the assignment
yes.
happen?
So if you remember, again, this is also optional, right? Because we usually render triangles. This is optional only when you want to render point clouds. So if you remember, there is also a variable in the fragment shader that defines the size of the vertex, right? Because the vertex shader works on vertices, right? So if you want to render a point cloud, you need to use that variable also on the fragment shader. You need to define a size for each vertex, right? It is usually defined, for example, depending on the distance of the camera, for example, but it can have different options, right? So let's imagine that you set a specific size for that vertex. That information is then processed by these other stages on the pipeline. I don't remember right now which stage in the end produces this specific variable input variable for the fragment shader. Right now I don't remember exactly which stage does that, but what it does is basically imagine that it treats each point as a quad actually, because internally if you want to render point clouds inside the GPU, they are considered like a rectangle, like a perfect square, right, on screen space. So depending on the size that you define on the vertex shader is the size of that square on the screen space. And so in the end, this is similar to what we do with fragment shaders with respect to triangles, right? If you're rendering triangles for a single triangle has a lot of pieces, well, a lot of regions, right? That are basically on the exact same location of a specific pixel, right? So when you are working with point clouds, a single vertex has a certain size, so it is a rectangle, well, a square in screen space. So imagine that its size on screen space is 10 by 10 pixels. It means that that vertex in particular will have 100 fragments, right? Because it represents an area of 10 by 10 pixels. So those fragments will have this information in particular, will have the information of its position with respect to that point, because you can use that information to change the color of that fragment depending on the position with respect to the point, for example. So imagine that instead of you want to render your point cloud, instead of showing every vertex as squares, you want to show every vertex as a circle, right? So you can use this point coordinate, right, to know at which distance they are from the center of the vertex, and you can basically discard the fragments that are basically outside a circle, right? I don't know if I was clear.
No, that's good enough. Thanks.
I will try maybe again. These questions are very important and is very relevant, and I can maybe add a little bit of a couple of slides on the next lecture talking about this point cloud rendering. It will be nice. Anyone else raising hands? Okay, Doruk, on mute. I think this will be the last question for today. Hi, Doruk.
Hello.
Hello.
I have already asked this in the chat.
Okay.
But I just want to make sure that I understand this correctly. What exactly are the inputs for Vec 4 on the next slide?
Sorry, again.
If you can go to the next slide.
Okay, next slide. This one?
Yeah. What are the inputs there for Vec 4?
Oh, okay. This is basically a color, okay? So they will be red, sorry, my mouse is here. Red, green, and blue, and alpha. Okay? Alpha, the alpha value is a transparency value. So basically, if your alpha is 0, it means that fragment color is basically transparent. If it's 0.5, for example, it means that the alpha value is like half transparent. This is very important because remember, we know the pixels are unique, right? Because we have a single pixel at the end, and in our monitor, a single pixel per coordinate. But fragments are not unique, right? For a single pixel, there could be a lot of fragments that are overlapping exactly on the same position. So imagine that you have, for example, 2 triangles that are basically overlapping, but one of those triangles it has alpha value. It is a bit of transparent, right? So basically, the color of your pixel will not have the color of the closest fragment, but a combination from the closest fragment that is actually transparent with the fragment that is behind that fragment, right? So the alpha value is used on the last stage of the pipeline to define the color of the fragments, also depending on the on its transparency, right?
I see.
Yeah,
Thank
but
you.
it's RGBA. Okay, good. So we need to wrap up for today. Thank you so much. I think this raising hand stuff worked. And again, remember what is already on the chat. Actually, when I stop the meeting, the chat will be gone. So please, if you really had something to ask and it was not answered by me or by Ibo, please go right now and post it on Piazza, and we can respond later. And yeah, and that's it. And thank you so much. And I will see you next Monday. See you, everyone.